All right, let's jump right into this explainer. For decades, we've relied on some truly incredible tools to peek out into the universe, right? Well, we are about to take a monumental leap forward. The Nancy Grace Roman Space Telescope isn't just a simple upgrade. It is an entirely new way of looking at the cosmos. It's going to fundamentally change our everyday cosmic perspective.
So, here's our roadmap for today. We'll start with how Raman is essentially Hubble's wide-eyed cousin, break down its anatomy, explore how it maps the dark universe, dive into the hunt for exoplanets, and wrap up with the big data frontier.
Part 1. Hubble's wide-eyed cousin and the incredible power of its wide-field instrument.
You know, the core problem with our current space observatories is that, yeah, they give us unbelievable detail, but it's kind of like trying to photograph a sprawling landscape through a tiny drinking straw. To understand the grand scale of the universe, we actually need to see the big picture. And that is exactly what Roman is built to do. Now, it uses the exact same size 2.4-meter primary mirror as the legendary Hubble Space Telescope, but its wide-field design gives it a view of the sky that is literally 100 times larger. When you look at this overlay on the Andromeda Galaxy, it just brilliantly illustrates the difference. See those tiny little squares? That is what Hubble gets in a single shot. But that massive pink grid, that's what Roman captures all at once. So a single image from Roman holds the exact same exquisite detail that would take Hubble 100 separate pictures to piece together. It surveys the sky 1,000 times faster, finally giving us a true panoramic view of the heavens. Moving on to Part 2, Anatomy of Roman. Let's look at the hardware powering this next generation.
You obviously can't capture sweeping panoramas like that without some serious technological muscle behind the mirror. To pull this off, Roman's wide-field instrument uses an array of 18 incredibly advanced detectors, effectively creating a massive 300-megapixel camera in space. And the beauty of this whole system is that it doesn't sacrifice any clarity for size. It maintains Hubble's crisp 0.1 arcsecond resolution, all while operating in the near-infrared spectrum, so it can literally pierce right through cosmic dust.
So where is this beast going to live? It'll be stationed 1.5 million kilometers away from Earth at the L2 Lagrange point, meaning Roman is going to be hanging out with the James Webb Space Telescope. And this partnership is absolutely vital. With its 5 to 10-year mission, Roman is going to act as the ultimate cosmic scout. It'll provide the crucial big-picture context and find all these fascinating targets for Webb to follow up on with its highly detailed narrow observations.
Part 3. Mapping the Dark Universe. Let's talk about the core community surveys.
Okay, so you have this massive, powerful instrument, but where do you actually point it? Well, Roman is going to dedicate the vast majority of its time to 3 massive core community surveys. First up, the High Latitude Wide Area Survey is going to map out a staggering 2,400 square degrees of the sky, studying weak gravitational lensing to trace dark matter. Then you've got the High Latitude Time Domain Survey, which is going to hunt for exploding stars, specifically Type A supernovae, to track how fast the universe is expanding. And finally, it's going to stare directly at the center of our Milky Way for the Galactic Bulge Time Domain Survey.
Which brings us right to Part 4, hunting for exoplanets and shining a light on dark secrets.
See, Roman isn't just looking out at the grand scale of expanding galaxies, it's also hunting for hidden exoplanets right here in our own backyard. And to find them, it uses this mind-bending trick called microlensing. Basically, by staring at millions of stars in the galactic bulge every 15 minutes, Roman just waits for a closer star to drift right in front of a more distant one. The gravity of that closer star literally bends the light around it, acting like a giant cosmic magnifying glass. And if that closer star happens to have a planet, its gravity creates this extra tiny little spike in brightness. It is so incredibly precise that Roman will use this technique to find thousands of exoplanets, and hey, maybe even some rogue black holes.
But wait, there's more. Roman also brings this groundbreaking coronagraph instrument to the table. You can kind of think of this as a pair of highly advanced, high-tech sunglasses for the telescope. By using deformable mirrors and these really complex pupil masks, it actively creates an opposite wave of light to completely cancel out the blinding glare of a host star. It's a technological marvel, really. It's going to allow us to directly image exoplanets and dust disks that are a staggering 1 billion times fainter than their host stars. 1 billion. That's just wild.
And finally, Part 5, the big data frontier, bringing the compute to the data.
So taking all of these massive panoramic photos introduces a totally new challenge that modern astronomy has never really had to fully deal with, an absolute avalanche of data. The magic number for this mission is 11, specifically 11 terabytes. That is the staggering amount of compressed data Roman will beam down to Earth every single day. Over its entire mission, it's going to gather up to 20 petabytes. To put that into perspective, that's the equivalent of roughly 10 million high-definition movies. Because that volume of data is so insanely huge, the old method of doing astronomy is practically dead. You simply cannot download these massive files to a local laptop for processing anymore. It just wouldn't work. It would be like trying to stream a 4K movie on a 90s dial-up internet connection. Scientists would spend months just sitting there waiting for a single survey to download. So a massive paradigm shift was absolutely required.
Enter the Roman Research Nexus. This is a brilliant cloud-based system built around one super simple philosophy: bring the compute to the data. Instead of downloading files, scientists are going to log directly into the cloud using open-source tools like Jupyter Notebooks, and they'll run their code right there where the data already lives. And honestly, here is the absolute best part. There are 0 exclusive access periods. The very second that data is processed, it is entirely open source. Anyone with an internet connection can access and analyze petabytes of non-proprietary data immediately. So, as we prepare for this monumental leap in astrophysics, launching by May 2027, we really have to ask ourselves, what dark secrets and hidden worlds are we going to find when we finally open our eyes to the wider universe? The Nancy Grace Roman Space Telescope isn't just going to take pretty pictures. It is going to map the very fabric of our reality. Thanks so much for joining me for this explainer, and as always, keep looking up.